Study,
Mark, and
action! So here we have an atom, and as we know, atoms have their own electron shells, and each electron actually has its own energy level, which is represented by a band. And the electrons which have the highest energy level, they form part of the valency band. But what goes beyond the valency band? That is the forbidden zone. But to understand the forbidden zone, we first have to understand the conduction band. So basically, the conduction band is an area in which electrons have to reach in order to conduct electricity. But there is a forbidden zone, which is an area in which electrons cannot exist.
Okay, so here we have the energy levels for a conductor, semiconductor, and an insulator. So the ability for any of these to conduct electricity is determinate from the forbidden zone gap. So in a conductor, there is no forbidden zone gap, so the electrons are free to move from the valency band to the conduction band. Hence, they can conduct electricity. Whereas in a semiconductor, the valency band and the forbidden zone is quite small, so it does need a bit of a potential difference for the electrons to cross the forbidden zone from the valency band to get to the conduction band, hence semiconductor. Whereas in an insulator, the forbidden zone is extremely large, so an extremely large amount of voltage is needed to stimulate electrons to move from the valency band to the conduction band, hence they do not conduct electricity.
There are two types of semiconductors, p-type and n-type. So we're going to discuss how a p-type semiconductor is made. So consider the lattice structure of silicon. Silicon is an element with a valency of 4. So you can see there's 4 valence electrons. Now in p-type semiconductors, a dopant, so in this case boron, or any other element which has one less valence electron, is introduced. So as you can see, boron has a valency of 3 and silicon has a valency of 4. When we introduce boron into the structure, it creates a hole due to one unpaired electron. And consequently, other electrons will move into the hole to try and fill it up. As a result, there is another hole. So another electron will try and fill up the new hole. This continues to happen, and the movement of electrons makes it a semiconductor.
N-type semiconductor, an atom with 1 more valence electrons is introduced. So silicon, which is a group for atom, have 4 valence electrons in its outermost shell. Then N-type doping, a phosphorus atom, which is a group 5 atom, is introduced, which means it has 5 valence electrons outside in its outermost shell. That means there is 1 valence electron, which is free, and it can move around anywhere it likes, anywhere it wants to go in the lattice structure. That makes it the semiconductor more conductive.
In an N-type semiconductor, the conduction band moves downwards towards the donor level. This is because through N-doping there is an excess of electrons in the valence shell, consequently requiring less energy for the electron to move across the forbidden zone.